Okay, we're going to continue with our stoichiometry for the first chapter in stoichiometry. Okay, so for this one, we have 3.94 grams of hydrated copper sulfate. It was heated, and 2.52 grams of the anhydrous salt remained. So we have copper sulfate that has water molecules attached to it. When it was heated, those water molecules evaporated off and the anhydrous salt remained. Anhydrous means without the water. So we've gotten rid of the water. Calculate the formula of the hydrated salt. So from this you should know that copper sulfate, CuSO4, and that's hydrated, so we have a dot with water. And I'm putting an X in there to symbol the amount, the ratio of water that's bonded to the copper sulfate. We don't know that, and that's the formula that we need to find out. Now that was heated, so I'm going to put heat over the equation line there, and we were left with anhydrous salt, which is the salt without the water. Okay, so that's the first step. Now what I'm going to do is I'm going to write in the information underneath. So I have 3.94 grams of the hydrated copper sulfate and 2.52 grams of the anhydrous copper sulfate. So this just makes it clear for me what I'm supposed to do now. So you can see that there is a difference in mass. So we've lost some mass going from the hydrated copper sulfate to the anhydrous copper sulfate. The difference in mass is equal to the mass of water that we've lost when it was heated. Okay, so the water is evaporated off. So if I take 3.94 grams and I take the 2.52 grams away from it, that's going to give me the mass of water that we've lost. Okay, so if now I have the mass of the water, whenever I have mass of something, I can immediately find out what the number of moles there are. So the number of moles equals mass over the relative molecular mass. I'm going to take that 1.42 grams that we found out to be the mass of the water and put it over the relative molecular mass of the water. So 2 times 1 plus 16 for the water, which is 18. And we're going to get 0.079 moles of water. Okay, so I also have the mass of the copper sulfate that was left. So the water has basically evaporated off and I'm left with the copper sulfate. I can also work out the number of moles of the copper sulfate that's left. I have 2.52 grams of it. And if I find out the relative molecular mass of copper sulfate, I can do it up here. 63.5 for copper, 32 for sulfur, and then 4 16ths for the oxygens. And that becomes 159.5. And I can work out the number of moles of the copper sulfate. Okay. So the copper sulfate and the water, these two, were originally together before it was heated in that ratio of moles. So that ratio is 0.016 of the salt and 0.079 of the water. Now if I want to find out the simplest ratio for this, we take the smallest number, which is this one right here, and we will divide across by the smallest number. that would give me a 1:5 ratio. Okay, and the 5 links with the water. That means for 1 molecule of copper sulfate, we had 5 molecules of water attached. And that is actually answered your question because you found out the formula of the hydrated salt. And that's it there. Okay, so I'm going to write up another one now and we'll go through this one. Okay, so here we have a chemical equation and our question is how much iron could be obtained from 30 grams of iron trioxide? Okay, so the question is how much iron, so how much of this substance right here, could be obtained if we had 30 grams of the iron trioxide. So the only two pieces of information is the amount of iron oxide we have and the chemical equation itself. So if I have a grams, I can find out moles. So we're going to go with trying to find out the number of moles of iron oxide present. So 30 grams is what we have. And then the the relative molecular mass of the iron oxide is 2 times the 56 plus 3 16s. And we get the number of moles to be 0.1875 moles of our iron oxide. So I'm going to write that underneath as well. 0.1875. Now what I really want to know is how many moles of this we got in the end. So that's where we're going to use our chemical equation for now. So if you see, we have 1 mole of iron oxide will produce 2 moles of iron. That's from the chemical equation up here. So that's a 1:2 ratio. And if I have 0.1875 moles of our iron oxide, I'm going to produce twice as much iron because it's a 1:2 ratio. So I'm going to take that 0.1875 and multiply it by 2. And that's going to be 0.375. So now I have the moles of the iron that's present. And if I have the number of moles, I can work back, look up here for a second, and find out how much iron in terms of mass was produced. So 0.37 moles of iron was produced. And I'm going to use this formula again. And it's relative atomic mass this time. So we're going to put 56 in the bottom for the iron. And we don't know the mass. So if you rearrange that, 56 times 0.375, you're going to get a mass of 21 grams of iron produced. And that's that question answered. Okay. Here's our question. What mass of ammonium nitrate would have been heated to make 550 centimeters cubed of this substance here? Okay, so that substance is dinitrogen oxide and it's at standard temperature and pressure. So I'm going to highlight the important bits. Mass of ammonium nitrate, this one here. And it's made 550 centimeters cubed of this substance, and it's at standard temperature and pressure. So our dinitrogen oxide is a gas. Okay, so I don't need to know that it is said in the question. I've just taken out some of the wording in the question. So that is a gas, and it's at standard temperature and pressure. And we know that 1 mole of a gas has a volume of 22,400 centimeters cubed. So that's important to remember. And that actually gives me a starting point for this calculation, because I have 550 centimeters cubed of the gas. And I can compare that to what 1 mole would be. And when I do that, it actually tells me how many moles of that gas I have produced. There it is. So I already have the moles. So I'm going to write that in underneath here. Moles of that substance. Okay, again we can use our equations. So how much of this was needed to produce 0.025 moles? And if we look at the ratio, it's a 1-to-1 ratio. So that means if I had 0.025 moles of that gas produced, I also required 0.025 moles of the ammonium nitrate. So let's look now at the ammonium nitrate. I have the number of moles, and I can work out the relative molecular mass, which will give me then the mass of the substance. So 0.025 equals the mass, and then the relative molecular mass is going to be 14 for the nitrogen, 4 for the 4 hydrogens, another 14, and 3 times 16, giving us a mass of 2 grams of the ammonium nitrate required. Okay, this is the next question. If you want, you should be able to try and do this yourselves now, so you can pause the video and give it a go. Okay, so again, we have a gas, oxygen gas, and we're given how much of that gas we have. So I'm going to write down my sentence again. 1 mole of any gas at standard temperature and pressure has a volume of 22,400 centimeters cubed. Now we have 700 only, so if I compare that to the volume of the 22,400 centimeters cubed that would have been in a full mole, I can work out how much of a fraction of a mole I have. When I do that, I get 0.03125 moles of the oxygen present. So I can write that underneath. Okay. It's asking me how much potassium chlorate I need. And you can see from the equation, it's a 2-to-3 ratio. And I'm just after working out how many moles I have of the oxygen. So I need to figure out how many moles of the potassium chlorate I need. So just to decide, 0.03125 links with the number 3. I need to figure out what number would link with 2. So to do that, you work back to 1. So you're taking that 0.03125, dividing it by 3, because we have 3 parts, and working out what that is, which is 0.0104. So 1 part will be 0.014. So I need to find out what 2 parts is. So I'm going to take that number and multiply it by 2. And we'll work that out to be 0.02. So now if I go back here, I can write 0.02 moles links up with the 0.03125 moles. Okay, so back to this equation again. The number of moles is 0.02. I need to figure out the mass and the relative molecular mass of the potassium chlorate is here. We'll do it on the side. So for potassium, we have 39. We have chlorine, and then our oxygen. So that's it there, which is 122.5. With a bit of rearranging, then you can find out the mass to be 2.45 grams. Okay, that's the end of the stoichiometry then. You might get questions where all of the previous examples and tutorials come into this, but you should be well able for them now.